Hi everybody and welcome to the 11th lecture of Digital Communication course. In today's lecture we will be talking about passband data transmission between two parentheses, basically modulation, how to transmit your data over a wireless channel. We all know that in order to transmit your data over a wireless channel, you cannot send your data bits that are generated by your computer immediately through the wireless channel. You need a signal that can travel through the wireless medium so that you can convey your data bits that you generated from your computer. And at the end of the day, whatever you generate, whether it's image or text or video or any kind of medium, you have to transmit it to the receiver, to communicate it and to let the receiver knows about what you are intending to send. So basically in wireless communication, in order to achieve that, what do? We try to encode the data bit information on a carrier that the transmitter and receiver can access and can see. An example of this carrier is sinusoidal signals. Sinusoidal signals, they can travel at a certain frequency, they can travel through the wireless medium. So the transmitter and receiver, the antennas of the transmitter and receivers can only understand and see or detect sinusoidal signals transmitted at certain frequencies, while the bits are information. They cannot travel through the wireless medium. So what's the solution? The solution is to utilize the properties of these carrier, sinusoidal carrier, let's say sine or cosine, and change them according to the incoming data bits. For example, what are the properties of sinusoidal signal? Amplitude. When you draw a sinusoidal signal, what do you get? Let's draw together a sinusoidal signal and see what are the properties. Everybody knows that sinusoidal signal includes sine and cosine mainly, and both are orthogonal to each other. So this signal, what are the things that I can change in it? Its amplitude, AM, its phase, from where it starts, phase, for example, this is with phase 0, this is with phase pi/2, and so on and so forth. You can make it phase of 45 pi/4. So you have the amplitude you can change, the phase and the frequency. For example, this is of frequency F0. If you increase the frequency, what will happen to this? It will oscillate more within a certain period. So you have these three main and key properties of your sinusoidal signal that you can play with, you can change. So what does this mean? This means that I can map my information that I want to send, the data bits that I generated from my computer, to specific changes in the features or properties of the sinusoidal carrier. For example, a smart guy, without I talk about modulation, can tell me, if this is the case, then look at me, I am going to make the following rule. When I have 0, when my computer generates 0, I'm gonna map it to sinusoidal signal with amplitude equal 5. And when I have 1, I'm gonna increase this amplitude and make it reach 10. So you send this through the wireless channel, through the wireless, and reaches here the receiver. The transmitter here talks to the receiver before he starts communicating and tell him, hey, look at me, I'm using this rule, this mapping rule. Whenever I see 0, I convert it to sinusoidal signal of amplitude equal to 5. And whenever I see 1, I convert it to a sinusoidal signal of amplitude equal 10. So the receiver understands the transmitter and saves this rule at his memory. This is the memory. He saves this information that this is the mapping rule. So the receiver, what the receiver receives a sinusoidal signal of this form. with different amplitudes. So when the receiver looks at this period, he sees a signal of amplitude equal to 5. Then, since he knows the mapping rule, he can make a guess now that during this period the transmitter sent 0. Now, when I come to the next period of the signal, I see that the amplitude of the sinusoidal signal now is 10. Since it's 10, and in the mapping rule 10 amplitude 10 equal to 1 represents 1, then the receiver understands that most probably the transmitter transmitted 1. So this is basically the first type of modulation. We can call it in amplitude modulation, changing the amplitude of the sinusoidal according to the data bits you want to transmit. And why do we call it digital here? Because if you remember from principles of communication, analog communication, we used to modulate the amplitude of the carrier by multiplying the carrier with the message directly. For example, in the analog, we were not using or dealing with data bits. We were dealing with what? With the message as is. You were not quantizing, not sampling, not having any data stream of bits. So when you used to have M of t, a message, and we said this can be your voice signal, you used to multiply it directly with the carrier. Cosine, let's say 2 pi fct, where fc is the carrier frequency. For GSM network, it's 900 megahertz. And the t is time, as function of time. M of t, you multiply it directly by cosine, and you get what do we call this modulation? Amplitude, double sideband amplitude modulation. This is in analog. Now we don't have such thing here. In digital, what's the difference? In digital, the message or the data we are transmitting, it's no longer analog. It's quantized and encoded. They are bits, zeros and ones. That's why the mapping should be between the bits and the properties of the carrier. So this is the first type of signaling or modulation, amplitude shift keying. The second type is to play with the frequency. Give me another rule for modulation. If 0 comes, then use this frequency. We fix the amplitude and we just change the frequency. This is the frequency. If not, and if 1 comes in the sequence, if the computer generates 1, this means that I'm going to increase the frequency of my carrier to f1, which is greater than f0. So the transmitter sends to the receiver, and the receiver at the receiver side, when he sees this frequency, represents it to 0, and when he receives this frequency, maps it to 1. Simple. The third type of modulation is to play with the phase of the carrier. So how do you play with the phase? For example, you fix the amplitude, you fix the frequency, and you start playing with the phase. You say, if 0 comes, let the phase be 0. The phase of the signal. The signal starts from here, from the origin, 0. If 1 comes, let's make it start from pi over 2. This is pi over 2. Yes, pi over 2 means 90. So when the receiver checks the signal, sinusoidal signal, and see that it starts from the origin, after it makes the synchronization and the estimation, then he knows that this is 0. But if it starts from pi over 2, this is 1. And by these rules that you establish, you can communicate your digital data bits using sinusoidal carriers. Simply like this. Now, what else? Think with me. What else you can bring? You can tell me, okay, what if I can change two properties simultaneously? The amplitude and phase, for example, together. In this case, I will be able to send more information. Here I'm sending, at each time, I'm sending only 1 bit. But if I change more than 1 property at a time, I can send more data bits. If I send more data bits, what happens? I increase the throughput, I increase the data rate, I increase the capacity of my network, which is good for our applications that require high data rate, like video streaming, augmented reality, virtual reality. Some applications, gaming, for example, doesn't require too much data rate. So you have amplitude, you have phase. Now, how do I determine which modulation scheme should I use? Now I have amplitude, I have phase, I have frequency, I have combination of them, amplitude and phase, amplitude and the frequency, frequency and phase, frequency and amplitude. How do I determine which modulation scheme should I use? Based on the situation, based on the conditions, based on the application. For example, suppose that your channel is full of noise, full of interference. Which modulation you use? Amplitude modulation or frequency? Full of noise and interference. What happens to the interference? Think with me. If you are sending an amplitude modulated signal, then your signal something like this. What if there is interference here? Your amplitude will become like this. So the receiver cannot distinguish this from this, because its amplitude is sensitive to interference. But if you are encoding your information in the frequency, what happens? The interference comes to the amplitude, the amplitude doesn't get affected at all. So in case the channel has too much interference, it's not good to use amplitude. It's better to use frequency, even if you use more bandwidth. This is the case, for example, to make you understand when to use what. Is this clear? We have 3 and the combination. You don't need to memorize anything. You just get the logic, the concept, and you apply it. And you get creative and innovative, and you can come up, if you understand the concept very well, you can come up with your own new modulation, and we can name it in your name. We can say Kirik modulation scheme, Ali modulation scheme. Why? Because you invented it. You came up with it. It's simple like this. Trust me, it's not difficult. If you get this simple concept, you can think beyond this and try to bring and innovate your own modulation. For example, one can think as follows. You teacher, you explain to us that we can use sinusoidal signal, and this sinusoidal signal only has amplitude, phase, and frequency. And you say that the communication systems in all over the world from 50 years ago, they are using this modulation schemes. So cannot we find different carriers with different properties and then send more data bits or different schemes? We have only sinusoidal, we don't have other things. This is a question that you can ask yourself, you can ask me, you can ask. This is the creative mind. Ask questions also. Says if he knows how this happens, then he start asking why and what if. And what if we can do this? What if we change the sinusoidal? What if we find another property in the sinusoidal? Cannot we send more data? And you come up with your own modulation scheme, just because you understood the concept simply, clearly, without any confusion. Trust me, it's not difficult. Once you get the concept, you become very innovative and creative. Let's see. If I give you, for example, a sequence, test you, now the time for test. Give you the following sequence. You are given, your computer generates the following data bits. 0, 1, 1, 0, 1, 0, 0, 1. And tell you, we are required to send this data using amplitude shift keying, encode the data bits into the amplitude of the carrier. And the rule is this: if 0 comes, don't send anything. If one comes, send a sinusoidal signal. So draw to me the resulting waveform. This is the question. The waveform that you see on the air that reaches your receiver, draw it to me, or you transmit at the transmitter side. You tell me when 0 comes, there is nothing, as you can see here, nothing. When 1 comes, I draw a signal. This is the signal. When 1 comes also, I draw a signal. And when 0 comes, there is nothing. Clear? Now I tell you no, I want to change. Amplitude modulation is not good because the channel has too much interference. It has too much noise. And amplitude modulation is not performing well. What do? I say, why don't I send it in phase? So in phase, I say if 0 comes, then send with phase minus pi over 2. You start from bottom to up. If 1 comes, you start from top to bottom. So this phase plus pi over 2, and this is minus. Now an engineer comes and tells me, no, phase modulation is not good. See, you are making quick jumps here. See the jumps here? You are making jumps here. These jumps creates problem to us. What's the problem? He says the problem, when you have jump in the amplitude, not transition, not smooth transition, you create interference. You create out-of-band emission. Your symbol, if it was supposed to be like this, then it becomes like this, interfering. Your symbols are back to each other. If it interferes like this becomes interference. You will not be able to detect the signal. He tells me don't use phase modulation. Think of another modulation. As a communication engineer, you tell him what about frequency shift keying? I think it works. If you want to avoid interference and you want to avoid noise degradation as well as out of band emission, you don't want your signal to interfere with the other pulses adjacent to it, so why don't you use frequency shift? He uses the frequency. What's frequency shift? He tells you if 0 comes, use a carrier with low carrier frequency. If 1 comes, use a carrier with higher carrier frequency. So this is the rule. When 0 comes here, you map it to this signal. When it's not squeezing itself, means the frequency is low. When the signal is oscillating too much, when it oscillates quickly within a period, this means the frequency is high. Because what's the frequency? What's the definition of the frequency? The number of cycles you complete within a time. Yes? The more cycle you complete within a time, the higher the frequency is. So here I can see that the cycles, the repetition of the cycles within a certain period of time increases. Due to this, I have higher frequency. And this maps to 1. Or actually 1, you map it to this carrier. And you solve the problem of your company in terms of sending your data reliably. This problem is usually faced by broadcasting companies. Like you are a reporter working in Al Jazeera or working with TRT World or working with TRT Hubbard, and you just they hire engineers like you to adjust the parameters of the transmitter that communicates with the satellite. For example, when there is noise, when there is degradation in the photo is not, the picture of the reporter is not showing very good, they just reduce the modulation, they change the modulation, play with these parameters just to make sure that the connection is always reliable. Ask your friends, some of them, I know one of my friends is working in Istanbul with a company like this, broadcasting. This company, whenever there is a live transmission, they go and set up the satellite connection, and he sits behind a computer and start monitoring the modulation and coding. He started playing with them fixing them, making sure everything is going properly, there are no problems, the connection is going smoothly, no interruption, and everything as you desire. So that's the application, one application or one possible future job you can get after your graduation if you understand these things. And they will ask you about this in the interview. What if we have too much noise? What do you do? What if we increase the modulation order? Now, what do you mean by modulation order? The modulation order, we increase the modulation. Now, in the next coming slides, we will explain what's modulation order and what's the effect of it on the performance metrics, like the error in your system or the throughput, the spectral efficiency, and this and that. Now, this is, if you understand these two slides, you understand half communication systems, half of the communication systems in the world. If you just understand deeply these things, because the others are built on top of them and just like different types of the same concept. The concept is the most important thing, but after that you start coming up with new techniques similar to it, but it provides slight improvements. But wherever you go, in any book of communication, the first topic, the most important topic they discuss is modulation. So if you get it here, that's why I said this is very important lecture. It's a lecture not to be missed. It's a lecture to be taken into care, and you must pay too much attention to it because it's very significant. And the science here, not only in communication, you can apply it to many fields, many fields. So, digital modulation techniques can be classified into two different types, coherent and non-coherent. Basically, in a nutshell, let's summarize them. Coherent means that you need full information about your carrier at the transmitter and receiver. What do I mean by full information about the carrier? You need the same phase, the same amplitude, same frequency of the carrier that you use for transmission and reception. Because at the end of the day, you decode your data from the carrier. Yes? And you must have perfect synchronization. Any missynchronization between the transmitter carrier and the receiver carrier, you end up not able to decode your data. You will have too many errors. This is coherent. Non-coherent, on the other hand, is a modulation schemes that does not require perfect synchronization between the transmitter and receiver. The carrier does not need to synchronize perfectly with the carrier of the transmitter. What are the consequences of this? When do you prefer coherent over non-coherent? Which one is better if these are the two schemes? Coherent, we prefer to use coherent when we care most about quality. So when you care most about the quality, it enhances your quality in terms of bit error rate and the throughput, but at the expense of complexity. Since you need and require perfect synchronization between the two, you increase the complexity of your receiver a little bit more. However, when your concern is simplicity, you don't want too much complexity, like for the case of Internet of Things applications, the devices are small, limited in resources in terms of battery, power, memory, computing, all these resources. The receiver cannot afford too much complexity, then you want something that's simple, then you accept to use non-coherent modulation. What's the price you pay here? The price is, since your scheme is a little bit simple, not that complex, then you will have some degradation in the performance quality in terms of error rate and throughput and capacity or something like this. So this is what I said. Coherent detection, coherent modulation has better bit error rate, which means it's robust It has immunity to noise, doesn't get affected by noise too much, but requires complicated circuit, as I just have mentioned, where non-coherent is the opposite of that. Clear is the explanation. See, I talk more than what's written in the slides. A lot more than what's written in the slides. So all this information to be taken aside, side note, because usually, as you know me, I only ask from the things that I talk about. I explain. Never surprised you with something I didn't bring. And usually I don't take questions from books. I don't take questions from... I create the questions from the things that I talk about, from the material that I give. So this is something to be remembered so that you don't repeat your mistakes that you have committed in the midterm. Good. Now, let's talk a little bit about M-array signaling schemes. Now, we said in the previous modulation schemes, ASK, for example, and FSK, PSK, P for phase, F for frequency, A for amplitude. Amplitude shift keying, frequency shift keying, phase shift keying. We call this digital modulation schemes. We noticed in the example that I just gave you, I have only two choices of mapping, either low amplitude or high amplitude, either zero phase or pi over 2 phase, either frequency equal to F0 or frequency equal to F1. But this is not very efficient because it doesn't allow me to send more data bits at each single transmission. So cannot I increase the number of levels so that I encode more data bits? What do I mean by that, increase the number of levels? You tell me, basically, what I mean is this. Cannot you have multiple levels so that they map to different data bits? For example, instead of having 2 amplitude level, cannot you have 4? 4 levels. If you have 4 levels, how many bits each level can carry at one time? If you have 4 levels, log to 4 is 2. Yes? Well, because in case you have 2 levels, then you have 0 or 1. Each level carries only 1 bit. But if you have 4 levels, how many bits these levels? 2. If you have 16 levels, how many bits each level can carry? 16, 4, exactly. So this is amplitude. Let's say this is amplitude shift keying. We have 4, since it has 4, we call it 4 ASK. Yes, clear? How many bits each level? 2 bits. We agreed on that. Now, the question is that, what happens when you have more levels? So I want you to tell me, when I increase the number of levels, when the number of levels goes up, what happens to the data bits that I map? They increase. More levels, more data bits for each level. What does this mean? This means that you increase the spectral efficiency, you send more data bits, you increase the speed of the internet, the throughput. But what this means also, if you increase the number of levels, yes, the receiver will have some difficulty in distinguishing between these levels because they will become closer to each other, very close. Any slide, when there is noise, the receiver might not be able to differentiate and distinguish between the different levels, and so that he cannot decode directly or correctly to the data bits. Good? So you have a trade-off. Now the conclusion is that when I use M-array signaling, the higher number of levels I use, the more data bits I can send, which means you increase the throughput, you increase the spectral efficiency. But the more difficult it will be for the receiver to differentiate between the symbols. Because, see this example, when you have only two levels, this or this, it's very easy for the receiver to distinguish between them. He only has two possibilities. The possibility of making error, how much? 1/2, half. When you have 4, the possibility of making error, 1 over the number of 4, 1/4. 1/4 for each one. Yes? So the total number of error increases. Because when you, how do I interpret this? Some of you, they didn't got this. They didn't get this very well. Let's explain it more. When you have two levels, the receiver receives 2, yes? He has to make decision between 2. So if he makes a mistake, he can be correct half and wrong half. But when the number of level increases to 4, what's the possibility that, and you sent this, the third one, what's the possibility that you decode this correctly? 1/4. And what's the possibility of making error? The rest, 3/4. So from error equal 1/2 to error 3 = 4. Which one is more prone, more susceptible to errors? The second one, the one that has more number of levels. Is it clear? Is it clear now, the trade-off? Tell me, okay, don't fool me. I am very careful here. When you increase number of level, you increase the throughput, you increase the spectral efficiency, but there is a price you pay. You increase the complexity of the receiver, and the possibility of error increases. And if I tell you, convince me, you just explain these things that I just explained. You tell him logic. Where do we use array? Now, if you understand this logic and this trade-off, and tell you are a communication engineer, I'm hiring you in my company, and look at me. I had a very amazing, very perfect channel between the transmitter and receiver. It's ADSL, VHDSL, there is no noise, the signal to noise ratio is 40, and I just want you to propose me a good modulation schemes that I can use over this. What do you suggest? A modulation scheme of higher order modulation, like 64, 124 levels, so that each level can carry 6, 8, 10 bits. Why? Why do I use this modulation? Because the signal to noise ratio very high. There is no noise. If there is no noise, the receiver can still distinguish and differentiate between all these different symbols easily, and still send more data bits per level. So, also, when the channel is limited, you know, bandwidth channel is money. You buy it for millions of dollars. We agreed on this in several lectures. We talked about it. So when you are limited in bandwidth and your application usually requires too much data rate, you have to use high order modulation so that you can provide high data rate. Even if you degrade, even if you encounter errors, for example, video and voice, let it go. The most important thing that you serve the customer. If a frame was an error, it's just a frame for a fraction of a second. So the modulation schemes that we design in this manner, we call them M-array. So in this case, what do we have? We have M-ASK, where M can be any value of power 2, integer power 2, like 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, and so on and so forth. 2 to power an integer value. Good. We are till now we are so happy about modulation. I mean, we feel like experts. Yes, we understand the tricks. We understand somehow the different aspects of modulation, how it works, how to use it, what are the differences between different types of it. We talked about M-array, MASK, MFSK. In MFSK, you use 16 different frequencies, whatever. M phase shift king, you use different. What's the good thing about phase shift? Each one has key property. Phase shift king, constant amplitude, good for peak to average power ratio, power amplifier. Amplitude shift king, good when you don't have too much noise. Phase shift king, good when you have interference and noise. So what works for certain scenario cannot work for the other scenarios. This is the beauty of it, that you have freedom in selecting between them. So these are the schemes that I talked about them. Now, also, you can combine two of them and have a new M-array modulation. Like if you combine the amplitude and phase together and use different levels, you end up getting what we call QAM, quadrature amplitude, the combination of amplitude and phase, and with M-array. We call them hybrid modulation. Why do we call them hybrid? Because they use more than one single property of the sinusoidal carrier. Amplitude and phase, phase and the frequency, phase and amplitude, this. Clear? Passband transmission model. Usually in communication system, we try to understand them by using models. So the model of wireless communication system, the simplest one is to have you have here message source, then this passes to signal transmission encoder to protect your data from the channel errors, and then you have modulator. In this lecture, we are talking about the modulator. And for this modulator, you use carrier wave, sinusoidal. And then you send it over the channel, and then you have detector. Detector is the one that's responsible for distinguishing between the different types of levels. Yes? And then you have decoder. We are here in this block and this block, usually we are talking. What's the difference between passband and baseband? In the previous semester I asked you, what's the difference between passband and baseband? Baseband, you are still in the low frequency range, around 0. You didn't use high carrier frequency. But passband, you multiplied. After you multiply with the carrier wave, with the sinusoidal signal, with FC. So this can travel through the air, through wirelessly, but this cannot. This is for wire, this is for wireless. This is after multiplying with a carrier. This before. Good, clear? So here, before this, you have baseband. After this, you have passband. Good, clear? The geometric representation of modulation signal. Digital modulation involves, you must choose waveform for transmitting a particular symbol or signal. And for M-array modulation schemes, you have M possible signals. Each level corresponds to a signal, and these signals, we put them in a set and call the first signal S1 of t. Now, to simplify studying these modulation schemes, we just want to give some mathematical notations so that we can deal with them and manipulate them and play with them. The first waveform that corresponds to the first symbol you want to transmit, we call it S1 of t. You have S2 of t, Sm of t. The element of S represents signal levels in multi-level M-array decoding. For example, when I told you have different levels, this can be S1, this can be S2. We call them just to name them mathematically, and this 4. And function of t, because this is function basically, and the x-axis is t. That's a waveform. For binary modulation, each bit is mapped to a signal from a set of signal set that has m signal. Binary modulation means you have only two levels or 2 different bits, and you map them to their signal, to their waveforms. Because as I said, you cannot transmit the signal, you cannot transmit the bits directly. You need to map them to waveforms and then modulate these waveforms. So what do? We have to send our information, we map them in a systematic way, and we use some basis function in order to be able to do so. These signals, the different possible waveforms that we use in the modulation process, we map them in a constellation diagram. For example, a signal in any location here in your constellation diagram can be written as a summation of weighted basis function. What's this phi 1? This is orthogonal basis function. Example on it, give me example. Sine. What's phi 2? Cosine. It can be cosine because phi, sine and cosine are orthogonal to each other, and since they are orthogonal, they can be used together. And this S1, 2, S1, 1, they are the weights. They represent the amplitude or where it's located. The general form, therefore, can be given as follows. If you have n number of basis functions, your resulting signal, the ones you transmit, is the combination of all these. Now, the math says that you can have infinity number of basis function. I mean, this is what theory says. But in practice, till now, we couldn't find a third basis function to sine and cosine. You remember that day when I told you we cannot integrate e to minus x squared and we call it q function? I told you if anybody can integrate this, he will make a breakthrough. Yes? Didn't we say we call this q function? Here another challenge here. I'm asking you to ask your friends who study math or your relatives or someone you know who's very good in math, who has multiple degrees, multiple medals, and got PhD and teaching in top universities. We have in math, we have sine and cosine, and they are orthogonal to each other. The challenge is this. If you want to challenge any mathematician, can you bring me another signal that's orthogonal to sine and cosine? If he brings you a signal that's orthogonal to sine and cosine, come to me directly so that we make a pattern for communication and say we found another basis function that's orthogonal to sine and cosine, and we can send more data bits, we can triple them. If you send 1, we will send 3. Imagine the implication of math. This is why we study math. See the beauty of math? Have you ever figured out where do you use math? Why do we study math? This is the beauty of math. If you find it mathematically, you can apply it practically, and the applications of this is extremely important, extremely useful. So this is what I wanted to say about this. So where are the basis functions? Can you draw them to me? Yes, as an engineer, I can imagine only 4 dimensions, 3 dimensions for geometry, and the 4th is time or frequency, because there is a relation. Can you imagine more than this? The theory says there are more. Dimensions are not limited to 4 or 5 or 6. There is infinity number of dimensions. But as a human, can you imagine more than 4 dimensions? I have the x-axis. I put one basis function, which can be cosine. And here I put another basis function. And here, third dimension, I put another basis function. Other than this, can you imagine a new thing? Can you imagine a new thing that's orthogonal to these 3? The theory says there must be others, but as we cannot imagine. Our understanding, our intelligence is somehow limited, and we cannot visualize in a clear manner more than 3 orthogonal basis functions, which we can usually, because this is our sense, this is what we see. We have the x-axis, the y-axis, and the z-axis coming out, 3D. But you know that we have 6D, we have 7D with virtual reality and this. But here in communication, how can you visualize this? If you can ever visualize that, then you will have significant impact on the field as well. So basically, if someone tells you, okay, I found the basis function that's orthogonal, you tell him, please give me the basis function. As an engineer, you are required to test this function and to see whether it's really orthogonal or not. How do you test the orthogonality of a function? You take the two basis functions that are claimed to be orthogonal, and you find the dot product. The dot product is basically, you take the first basis function and the second basis function, and you multiply them with each other. If the result is 0, if the result is not 0, then they are not orthogonal. The dot multiplication of 2 orthogonal basis functions must be 0. If it's not 0, this means that they are not orthogonal. Clear? This is the orthogonality condition over a period of course, over a complete period. The energy, how do you find the energy of basis function? The energy, what's the energy? We consider the signals here as electric field, current or voltage. Suppose this is voltage phi. How do you find the power? You square it. You assume 1 ohm resistor, and then to find the energy, you multiply with time. Well, since we have functions here, we integrate over time. So this is the energy of the basis function. If its the maximum amplitude of the basis function is unity, if the basis functions are normalized, then we call it orthonormal basis function. Clear? Orthonormal. The basis functions can be found by using a procedure called Gram-Schmidt Procedure. Gram-Schmidt Procedure, I think some of you studied it in linear algebra. This is math subject, just teaches you how to find basis function orthogonal to each other. Okay? So, with this, we stop here. And thank you very much for your attention.